policy and a very expensive and complex decision process, right? I bet you there might be 2 people in this room that could list the tie-breaking steps in BGP in a common implementation, right? There's a dozen. So instead, we consult the professor, probably one of the world's most famous computer scientists, Edgar Dijkstra, who developed the shortest path first algorithm, which is what ISINS and OSPF, notice the SPF, both use. So what we're going to do is take this quietness and the scalability of BGP and use the path calculation of ISIS, okay? And have something we call BGP SPF, okay? But I thought BGP was path vector, not link state. Okay, how does this work? Well, it's a new SAFI. The NLRI format is the same as BGP link state. Okay, it runs Dijkstra instead of best path. Okay, it can do multipath, new SAFI, and LS node attribution. It has the peering models of IBGP, EBGP, and route reflection. You can do them all. Essentially what happens is BGP Classic has this monstrous decision process here in the middle. Okay? And this is greatly simplified. And you take it out and you throw it away or save it for next week and replace it with SPF. Okay? So, the next hop and path attributes are free with the LS address family. Okay? You need them for error handling and error reporting. Okay? The best path decision processes are replaced by SPF, aka, Dijkstra's shortest path. Phase 3 tiebreaker may be skipped as the NLRI is unique per speaker. You want the most recent version because it's always used and re-advertised. And you have sequence numbers for replay issues, etc. Okay? You start with a very simplified SPF with point-to-point only links in a single area. It should scale well for most use cases. Okay? You can support computation of LFA, segment routing, all the other fun features people are putting in BGP because they wouldn't fit in DNS. Right? And the link state address families, dual stack, v4, v6, VPNs. It even washes your car. Okay? It has the peering models you're used to with BGP. There's just one issue, which is, of course, you need to figure out the link state between 2 devices, and you want liveness detection outside of BGP. Route reflector hierarchy can be less than fully connected because you've got SPF to help you. This is a change. Okay? The controller can learn the expected topology through some other means. Okay? So, by the way, this paper reference here is a delicious paper. Cisco's Jupiter Rising. But they're use centralized control. This is distributed. And the point is, BGP is doing the shortest path first topology discovery, but how does it discover the topology? How does it learn what the links are and what the addressing is? So every rack is often an AS. We have to get over it. It was a shock to me. Okay. But how does it learn the link state? It needs to discover the neighbors between two devices. That's all. It pushes it up to the SPF algorithm, and BGP discovers the topology. LLDP looked like a good candidate, but it's complex, and it has IPR above 1,500 bytes. And you're going to see applications of this that go above 1,500 bytes between here and the next IETF. So we wanted something simple and saw no real need for the complexities of CLNMP, et cetera. So it's a new ether type, and it's got ether payloads. It's all over ether framing. And it kind of looks like this. It's Ethernet PDUs between devices, just that link. And they tell each other the link state over this link. Hey, I've got this addresses on this interface. Hey, I've got these addresses on this interface, et cetera, et cetera. But that doesn't transfer this information here. It's going to push it up. And here's going to be the topology discovery, up in BGP-LS and BGP-SPF. Okay? You just do you throw in a liveness check because it comes real cheap and free. And BGP-SPF uses link state to discover and build the topology database. It's just got all the links. Now it has the topology. It can build a topology, and it can run SPF. I'm not going to bore you with the East-West protocol. It looks just like most IETF protocols, all these little diagrams with all these little packets. Okay? And in this case, all the little packets are about, hey, this is my identity, this is my MAC address, and here's the IPv4 encapsulations, here's the IPv6 encapsulations, here's the MPLS v4, MPLS v6. Right? Pretty simple. What I like about this is, it's pretty dumb and stupid. And that kind of works for me these years at my age. So, it has the link state topology. It pushes it up through RFC22 API to SPF. And that's the end of it. That's all that happens. And you've got routing that scales to very large data centers. And unlike a bunch of other stuff in the space, and here it is pushing it up the stack. And unlike a bunch of other stuff in the space, there's no IPR. And there's no more slides. That's another way of saying questions, or answers would be better yet. This, for those who want to dig more deeply, is all in the LSVR working group of the IETF. There are two main documents, which one is BGP SPF, and one is the Ethernet Discovery Protocol, LSOE. Thanks for playing.
Yeah, thank you very much, Randy. No questions. So we can get off free with that. Thank you. So just before I invite Frank Martin up, just a reminder of a few things. We have call for lightning talks is open. So lightning talks take place on Thursday afternoon from 2:30 p.m. It's a Thursday afternoon session. We've had a few submissions already, but we're still having a few more. The PC will be looking at those. We'll make the decision by the end of the day on Wednesday, so you've got still a couple more days. We pick the best 8 or 9 talks, so if you've got anything that you'd like to talk about that's relevant for the community and internet operations, or something that will impress the PC, go for it. Next presenter is Frank Martin from LinkedIn. Frank is going to talk about IPv6 at LinkedIn. hopefully we can get some questions for Frank about his presentation. If you want to walk around, just
grab the mic and the cue.
that thing there.
All right. Yeah. All right. So I have a strong French accent. So if you don't understand me, I will not take my American accent. So IPv6 at LinkedIn. So it's a journey. We look back in 2012 and we say, okay, the world is going to run out of IPv4 in a couple of years' time. So what we did, so Jeff, who's here, did this nice graph, and we saw that for ARIN, the region we are in, that will have an end of time. Other regions have decided to have emergency IPv4 allocation, but for ARIN it was coming down hard, so we wouldn't be able to get new IPv4 address except on the secondary market. So we needed to move on, and we needed to provide IPv6 on the site. So providing IPv6 on the site, it's standard practice. Maybe you've seen it before. You put a proxy in front of your IPv4 servers, and this proxy will convert the IPv6 traffic that you receive to the backend, IPv4. What we did is that we put the mail first on IPv6, while the backbone was IPv6, and the mail at the time I was postmaster, and I was managing all the servers, so that was a decision of one. The difficulty when you put mail on IPv6 is that you use a lot of IP reputation, and when you go over IPv6, and you've multiplied your database of IP reputation by billions of times. So the way to do that is you get away from IP reputation and you move to domain reputation. And a lot of the mailbox provider, you take Google, Comcast, LinkedIn, Microsoft, then at the time, we set up that if you're not email authenticated over IPv6, we will refuse the email. You can try again over IPv4. So for IPv6, we put the email on in 2013 on IPv6, and we put the site on in 2014. We miss, I think, by a year the IPv6 day set up by Internet Society, but we got it up and running. One thing also that when you enable IPv6 on your site, you need to have your office with IPv6. Or do you know your site is running if none of your engineers can access it over IPv6? So also that's a part. Put the office over IPv6, put your engineers so they can see the site too. A little bit of stats. So I took about 1 year of data for page view, and then you see that IPv6 is growing. That's worldwide view from our side. You see that there is a weekend effect. I think that's the next frontier for us to build IPv6. So people are at the office. Office have got IPv4, and then they go home, and then they have got IPv6 at home. Or they are on their mobile. They're at home. So you've got the weekend effect, where IPv6 in percentage is higher on the weekend. In terms of traffic volume, usually it's lower. But in terms of percentage, you've got more IPv6 in the weekend. So the next frontier for us is get IPv6 inside the enterprise. Let's look a little bit on the region. So I took 3 countries, India, Japan, and China. One thing interesting is India has grown rapidly. Reliance Jio providers in India has grown a lot with their customers, and their network is IPv6 only on their mobile carrier. And that's created a lot of growth. Japan has been deploying IPv6 very early, and you see that it's a constant growth, but Japan started very, very early on IPv6. China started very recently. So last year, China decided that they need to put everybody on IPv6. And they kickstarted initiative within the Chinese government with all the telco providers to get on IPv6, and we saw the start. That was in September? Oh, sorry, June, July. In July, we saw the start of China going IPv6, and they're growing rapidly. One thing I like to point to is that these are percentage, but when you convert in terms of number of people, that could be really interesting. So for instance, in India, I think Internet Society say that there are about 200 million users on IPv6 only mobile. And in China, if you compare these numbers to the number of people, 10% is a lot of people, a lot of devices already on IPv6. What's also interesting is that it's all mobile. That's easy. It seems that going IPv6 on mobile is the easiest path. You don't have to go and change all your gateways, all your premise equipment that are in various enterprises, that are in home. You've got a high rate of renewal of mobile phone. Every year you get a new one. So that's a path which is easy to convert over IPv6. Also, the various providers, so if you go iPhone or Android, have decided to set a program to be IPv6. So all the application is to be able to work in an IPv6 only environment with NAT64 to reach to the NAT64 XLAT or etc., but to be able. All right, so that was some stat. Things that we found out also is that IPv6 is faster than IPv4 in some of the case, in many cases. Is it due to the network is newer, cleaner, there's less error? But what I would like to point to, whatever is the reason, the advantage of IPv6 and IPv4 is that you've got A/B testing. Now you can compare the performance on your IPv4 network versus your IPv6 network, and then you can ask question, why I've got difference of performance between the two? It's going on the same wires. So what's the difference? All right, in 2015 also we saw that we are going to run out of internal IP space. You know, the private space, as in 1918. So we needed to start to do something. So we set up a working group for the data centers, and we say, okay, we are building a data center, so the next one that we'll do, we'll try to do it IPv6 only. We set up this data center, which is in Oregon. If you look on YouTube, there's a couple of videos presenting it. We deploy IPv6 entirely in this data center. What we didn't do yet was to put Quad A. So all the machines have had IPv6. If you look in your standard Linux Windows servers, they are already running on IPv6. The local link is enabled. The IPv6 stack is enabled. You just need to put a global address. For applications, they are already on IPv6. Why we wanted to go IPv6 is because in the DC, then you started to scale. So we started to have, one server across the racks, and you had multiple servers for the same unit, and then you started to go virtual compute, so you had containers of containers within inside the server. So you multiply the density of your data center. So despite you've got the networking that already show, but then when you add container within the servers, things are becoming interesting. Also, opportunities, we are not constrained by the IP address. We can deploy, we don't have to play tricks, we don't have to play NAT inside the data center. And we have end-to-end connectivity from the office to any of the servers if you want to. Okay, reminder, if you want to go IPv6, both machine needs to have an IPv6 address which is routable on the internet, and you need to have a Quad A. 3 pillars: network, hardware, software, when you want to go at IPv6. You are network engineers, so network is done. You know well about it. Software engineers, try to find a course for software engineers about IPv6. Engineers, they just, I'm opening a socket, I send a message, it arrives on the other end, what could go wrong? So you need to have software engineers that understand network, that understand the different particularity of each software language. How do you open a socket that listens on IPv6? How do you make a connection prefer on IPv6, etc.? So there was, I think there was only one document made by Epinic, I think, on software engineering. with IPv6. And that's the part which is a little bit missing to get more on it. The other pillar is the hardware. And that's the part that we sometimes forget. I'll come to it. So on the network, we tend to use static IPv6 address. So when you've got this big data center that Randy showed, it's easier to, at build time, to select the IP address. A little trick that was given us by Facebook, which is interesting, use the local link. FE80 column 1 as your default gateway works everywhere. You don't have to worry on which switch you are, what's the network. You use that on the server. You just configure your switch for it. Like this, you don't have to change the configuration on your server all the time. Tools, you need to convert your tools from IPv4 to IPv6. When you are deploying at scale, then you need automation. You know, when you have got large data center, you want to be able to build hundreds of servers, thousands of servers at a time. So you need to change your tools. Also, what we did when we did this conversion, so we found a mapping between IPv6 and IPv4 so that we could use this mapping in many other tools. So you have to do a mapping, so we use, we've got a piece of software that tells us for this network, the equivalence between IPv4, for this IPv4 network, the equivalence on IPv6 is this network, and vice versa. And then usually we use the last byte of the IPv4 as the last byte of the IPv6 for that. Why we do that? You've got ACLs. You've got networks, you've got tools that are moving between all these two. So if you have got ACLs deployed, you want the same ACLs deployed on IPv6 before you have deployed anything on IPv6 yet, on servers. So that may allow you to create all your ACLs that you need in advance, if you have this mapping. Once you have passed the cap of dual stack, and fully dual stack, and then you start to remove IPv4, then you don't need this mapping. But until then, you need to be able to make this move. Let's talk about hardware. So that's the frontier. Firmware. So I like to talk about this one specifically. So when we get a server, normally the depreciation rate is about 3 years. So you get your server for 3 years. You get your network equipment for 3 years, at least. You can carry it longer. So that means that the firmware that is on the server that allows you to boot it from the network, a server has got nothing. It needs to boot from the network. You need to find its beginning of operating system. So you need to network boot. You can't do it with the BIOS. BIOS doesn't support IPv6. UEFI support IPv6 network boot. So you need to change your legacy boot to UEFI boot. Then you need to use IPv6 network boot with a PXE. And then you need to have tools like Grub with IPv6 support. All right? So we tested it. We were able to do it, but within the Grub at the time, we had to package a complete image as a RAM so that it could be unloaded on the machine and booted from there. So the IPv6 support is weak. You've got many protocols. So in your firmware, when you do the network boot, are you going to get DHCP for the IPv6 address, or are you going to use Slack? Or do you get your DNS server? Are they coming from DHCP, or are they coming from the DNS, the RR record? So that's a question. Other part, the BMC and the IPMI. So that's the out of band or in band that you use on the network interface to control the server. So IPMI allows you to pour on, off the servers to see what's on the screen via the BMC interface. That's another piece of firmware. Redfish, a new standard, support IPv6. All right? So we've got all these new firmware that are coming through. They are a little bit weak and tested. And you've got them for the next 3 years. Because when I go and say, OK, I would like to flash 1,000 servers, they look at me and they say, no, go away. OK, because in general, it goes well. But sometimes you end up with a brick. And so that's the difficulty of flashing firmware. And you may have seen with all the security release on Intel where you had to patch some code and do some crazy stuff. Flashing firmware or changing the firmware is a little bit crazy. It's a little bit difficult. So it's always dangerous to flash at scale. So you want to have these servers with UEFI network boot, with the right set of DHCP or Slack protocol in it. You need to have Redfish in the servers. If you don't have that, for the next 3 years, you will have difficulty to migrate IPv6. All right, software. So that's a part of software engineering. So is your software listening on IPv6? So all the pieces of software that you have that are listening on IPv4, are they listening on IPv6 also? Because as soon as you put the code in, then they will receive traffic. Are they ready? Connect strategy. You saw on the browser that we've got IP eyeball. So you make 2 connections, one to IPv4, IPv6, and which one resolves first is a winning one. That's very nice. The trouble is that when IPv6 goes down, nobody knows. So it's useful because you don't have a hard fail, but then there's nobody there that knows and here to fix it. So sometimes you're wondering, okay, should I do a hard fail? Because that creates an event, then that creates everybody on deck to come and fix it, versus a soft fail that is only seen if you're monitoring. Most of our stack in Java, Java's got some specificity which are very nice, is that there's a switch to enable IPv6. So Java will listen on IPv6 all the time, but you have a specific switch to tell it, okay, now I want you to start to make connection over IPv6. So the advantage of Java software is that you can deploy it in dual stack environment, and when your application is ready, you can flip the switch. Okay, deploy IPv6 ready. That's a big term when you ask people when I go to see engineers, is your software IPv6 ready? Oh yeah, sure, sure. You don't know until you test it. Put it out there and then you figure it out. Oh yes, this connection is a protocol to communicate between the 2 nodes to exchange information and admin message. Oh yeah, it's IPv4 only. Change the engineering culture. So that's a little trick that we like to play. You need to get your engineers used to IPv6. So there's a couple of people, mainly in the room, then we do IPv6 because it's fun, because we want to do that, because it's part of our spare time. So we deploy IPv6. But you want everybody, every engineers, to work on IPv6. It should be part of their success factor for their set by the management. So that's when you're changing the culture. When it's part of software development of practice that everybody should code for IPv6. One little trick that we did that was a colleague team found that. You can configure SSHD to refuse connection if coming over IPv4. There's an ICALL type, so you can say to people coming on IPv4, I'm refusing the connection. So you can't SSH to servers if you are coming over IPv4. So they are asking, why I can't connect to that? Well, you need to change the switch on your software to go over IPv6. Or my desktop server or my laptop doesn't work with IPv6. Well, why? So you get into the state of hard fail. So don't do that without testing and checking and monitoring your whole environment. Once you say, okay, everything is IPv6, then you can do it. So like this, when there's an IPv6 outage, it's visible and people come and fix it. Okay, takeaway. So we moved our staging environment to dual stack with ANA. We are retrofitting on production, so we are at about 60%. We are using the normal depreciation rate, so we set up all new servers coming dual stack. So as they get changed and renewed, so today we are about 60% in production. We still have some lingering issue with various pieces of software, so you need to find them. Couchbase resolved it, was it this year or late last year? So they are fully dual stack now. We've got some stuff in Zookeeper, and Hadoop is still very much IPv4. However, it can work on the dual stack IPv6, and there is a branch which is IPv6, but not fully tested. It's okay for Hadoop because it's its own, I call it sandbox. So all the Hadoop servers are their own environment, and when they need to communicate to the outside world, they have got gateways over IPv6. Remember, we don't want to deploy IPv6, we are here to remove IPv4. So don't forget the end goal is to remove IPv4, not deploy IPv6. You need to measure. So constantly, every day, we run a track of asset, how many servers in the whole our environment are with IPv6 address and with query record. Know all the unknown very early. If you have a firmware that doesn't support IPv6 and you start to talk to your vendor, the time the vendor starts to acknowledge, 1 year. The time you will get a solution, another year. The time it's production ready, another year. Okay? So you need to do your inventory as soon as possible. Okay? Know your unknown, know which software, which one are the blockers, which one you need to start to talk. So we are a group, several people have started. Facebook converted their old data centers. I think Google is on the IPv6. There's many companies that are working on IPv6 deployment. So if you are getting there, there's a lot of things that have already happened. There are a lot of change that have already happened. But try to do your inventory as soon as possible. Try to find the problems because you will need to talk to vendors. You will need to talk to people. It's silly when you start to flip the switch and somebody say, oh, this software doesn't work. No, you have to revert back your change and then wait till that software gets fixed. Don't relax or forget you have IPv6 because with IP eyeball, it will fail and nobody will notice. And then what you establish as IPv6 in the standard is starting to deprecate it. And then when you start to want to work with it again, then you realize that it's not in the state you had it before. Engage top-level management in its buying. I feel we need more software engineers today than network engineers. If you don't know, if you're a network engineer and you don't know what IPv6 is, I think you need to find another job. Okay, and build a Quad team. Thank you. Questions? Before people thinking about questions, I've got some nice sticker on the table. If you want to have an IPv6 LinkedIn sticker, come and grab it on the table after the talks. Wake up. Oh, here we go.
Hello, hi, this is Raj from Bloomberg. I guess in one of the slides you mentioned that you set up like a work group. So I was wondering if you can share some details as to which teams other than the network teams you needed sort of the buy-in to start pushing this across the board.
All right, so if you're doing it externally, then you need to If you're doing it externally, then you need your traffic people, you need your database people because they will store IPv4, IPv6 address everywhere, so you need to find where this is stored, and the network people. So traffic, software engineers that are just on the front end. Once you do it internally, there's a lot of more people that you need to involve. So the network people, the system administrator, you need to convert these servers. You need to get your SRE, service release engineer. So they are the people that are deploying the software that the engineers are producing into the servers. So you need them on board because they will need able to, they like to know, okay, what this change, what he will do. Let's make the change. Let's verify that he did what he was supposed to do. You need to get the engineers to fix the software, and you need to get your security also on board, because suddenly you're changing what's happening in the logs. So from IPv4 address, there's IPv6 address, and they will have to figure it out where this traffic is coming from, and also all the change.
Thank you.
One more? You can't go till somebody else asks a question. No, not really. All right. So remember, get your firmware right.
Thank you very much, Frank. I'm surprised, so few questions. So as Jeff comes up to the stage to tell us about time, I apologize for the room being so dim. It's because the projectors are very dim. We are replacing them. We'll have new projectors tomorrow, so please bear with us. I realize that the webcast is not very bright, but I have to turn the lights down so we can actually see the slides on screen. So apologies to the previous two presenters and to you, Jeff. I just hope it doesn't spoil the experience. It'll be all good tomorrow, I've been promised.
Thanks, Philip. Hi, I'm Jeff Houston. Look, just open your laptop and look at the slide presentation there, or read your email, or do whatever you want. It's cool. I too have to apologise. I got some disgusting lurgy in San Francisco and I'm sort of dying on my feet, but what the hell. This is an odd kind of talk because it sort of came up from work I was actually doing in part of security, and it sort of came up by accident. And the first part of this talk is actually a little bit of an exploration into one of the things that we always assume we understand these days, time. So I actually want to talk about the nature of time and what time really means in this age of computers, and then talk about the fact of how accurate is your time. Like in theory, my Apple machine says 17:26 and some seconds. Does yours say the same? And if not, why not? So let's go through this and just sort of have a breeze through time and see what we can find out here. Every single computer, every single one has an oscillator, right? You'd call it a clock, but it's not a clock. It's just something that goes bzzz at some vague frequency. And this clock manages the state of your central processing unit. So every time the clock goes ka-chunk, you do a memory fetch, you do a register cycle. Do you remember those old computing science courses, those of you who did it? This is all about the way a computer actually works, is that it goes from steady state, clock tick, to the next steady point, clock tick, to the next, to the next. So one cheap way of doing a clock is you take this oscillator and run it through a counter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all of a sudden you have something that gets bigger over time. And that's the way we originally did conventional clocks. Easy. So why do we have clocks in a computer? Well, obviously, we kind of wanted more than just run the computer. We went, run this job at midnight. Run this job at 2 minutes past 3. Run this job every 5 minutes. So all of us are used to cron tab in one way or another to simply schedule jobs. But there are other parts that are more subtle. I'm not sure if any of you know you run NFS these days, but most of you run some kind of networked file systems, some cloud store. Is that the right word these days? I don't know why this man is aiming a mobile phone at me. Some cloud store or some other thing. How do you know whether the file in the cloud or the file on your drive is the most recent file? Well, you look at the file creation date and times. And sometimes to make this work properly and not get hopelessly confused, you both need to agree in time more than hours, more than minutes, down to milliseconds and finer, just to understand which is the most recent. So time is important. But it's more important than that. The fundamental language of security, oddly enough, is time. This is my certificate. That's too fuzzy, I can't read it. But at some point in the future, that certificate won't work. But that time in the future is not an absolute thing. When your clock in your machine is greater than that time, don't accept this certificate. So if you dial your machine forward in the future and present this certificate, your machine will go, no, that's a dud. No matter where you look inside secure systems, you're going to find time. Google run for www.google.com a 90-day certificate. So if your computer is out by 90 days, you're going to have a pretty hard time trying to understand what Google is doing, because everything they do is going to be invalid according to your clock. So time is important. We need to keep time. We need to maintain it. But this is really getting bizarre, because the one thing that we've managed to do with computers is take them out of that air-conditioned, temperature-sensitive, constant humidity clean room and put them in your backpack and my pocket. And there's one thing about my pocket, try as I might, particularly at the moment with the flu, I am not temperature constant. And because my temperature is not constant, the oscillator will vary, because oscillators vary according to the external temperature. So that quartz crystal that's busy going hum will hum at a different frequency if the temperature goes up or down, right? So changes in temperature change the clock. Now, the other thing about my computer is it's got more to do than just counting the clock ticks. And some jobs are more important. Whoops, the clock's ticked. No, I'm sorry. I'm doing some massively important task. You're lower on the interrupt stack than me. Go away, clock tick. And so computers do tend, from time to time, with no other factor, they lose time, because basically they lose interrupts. So, you know, time on a computer is normally a variable thing. I might be one of the few, I know there are others who worked on mainframes, but way, way back before networking, and it was all about mainframes, clocks always drifted. So it was always a task at some point, quite regularly, to either ring the phone, if there was a phone service that did the time, or some other external time source to basically retime the underlying registers of time inside the machine, which was kind of dubious accuracy, but without a network who cared. But what we wanted to do was to make the timekeeping better. So this is an early slide by Dave Mills, 2001, just looking at what happens when you don't keep time. He was looking at his own machine over a 1-week period using Linux and noticing that because of temperature variations and load variations, the clock just swung up and down in terms of accuracy, and that's pretty standard. So what do we expect out of time? What do I expect out of my watch? I want two things. Interestingly, a second should almost always be a second. Unless someone wants to talk about leap seconds, we'll say a second should always be a second. The duration of time in a second should be the same for every second. You can't have variable in seconds. That's not part of the rule. And the other thing is, I want not only stability, I want accuracy. If we all, if we're all keeping the time, it should be the same time. So I want two things. I want the time to be constant, stable, and accurate. So, okay, I know what I want. What am I talking about? At this point, life gets weird. You know, it was a good thing a few thousand years ago to figure out that summer was summer and winter was winter and the other things were a bit in between, and that was fine. When we started doing railways, all of a sudden, accurate time became important, not the least of which to understand if I sent the train north at 3 o'clock in the afternoon and someone sent another train south at the same time, there was going to be a horrendous crash. Things needed to synchronize a lot better than what we were doing. So what we started to do was simply take the time the Earth rotates. So you look at the sun, take the highest point, and measure the amount of time it takes for the sun to be at the same point, the highest point in the sky, the next day. Divide that up, 24 hours, 60 minutes, 60 seconds, off we go, and we're done. All of the geologists in the room would go, that's bullshit. And all the astronomers in the room would also go, that's bullshit. Because the one thing the Earth doesn't do is rotate at a constant speed. It wobbles. It wobbles quite badly. There is a lot of variation in that measurement. The epoch point of the sun changes a little bit. So enter physics. I looked this up just a few minutes ago because I think this is just absolutely batshit weird. At the centre of a large active galaxy, and the good news is we don't live in a large active galaxy because we'd know it. At the centre of a large active galaxy is a massive accreting black hole. And that black hole has an accretion disk around it, because that's what black holes do, evidently. That accretion disk focuses the matter pouring in, and because as it pours in, it gathers enormous amounts of energy. Some of that energy is emitted back outwards as an astonishingly bright beam. We call these quasars, and they're some of the most distant things we know. They're as bright as hell, and because they're so distant, they don't move. So the next standard of time we used came from the astronomers in the 1960s, and it was based on a reference collection of 40 quasars. And when those 40 quasars are at that position, that's, if you will, midnight, or some other reference point. And when the Earth spins to the same quasar position, you've just done 86,400 seconds. Exactly. And so we used astronomical time for quite some years. But the Earth wobbles, this is no longer any good. We want even more than quasar-based time. So the nuclear physicists said, if I get a rubidium laser or a hydrogen maser or some other equally cool source of energy, and I get a cesium-133 atom and I excite the crap out of it, it oscillates. And it oscillates not just of it oscillates at 9,192,631,770, not 771. Like, this is just weird shit. But now I've got a clock that works right down in the nanosecond area. I heard scientific press a few months ago, they're now trying to even greater orders of magnitude with something that oscillates at an even greater rate. But for our purposes, that's a pretty cool degree of accuracy. Cesium clocks are amazing. Now, you can probably buy one, although I looked now and I can't get one on eBay this week, but you know, you can probably, if you look hard enough, you can get one. There are little ones that are inaccurate. There are things like that that cost a lot more money that are really okay. And if you're really lucky, you can find a spare hydrogen maser clock if you really want, but you know, you need to have friends. So not all of us can run these, but oddly enough, there were a few folk, and one of them happened to be in the US. And these kind folk strapped up 31 spacecraft, each with their own cesium clock, and called it GPS. And that's what actually most of us use these days. The Europeans launched Galileo. I'm not sure how useful that is. GPS forms the mainstay of this these days. 31 of these operated by the Air Force. Cesium clocks, they get replaced once every, I don't know, decades or so. And if you can get a multiple set of signals, each of which are sending you accurate time, then the rest is simple mathematics. You know where you are on the Earth, and you know the time. And that's why all of us basically agree on the time, because all of us use that time as the basic source. Now, a GPS receiver needs to see the sky. Shit, there's no sky up there. Most of the time, you put computers in computer rooms or in your pockets and so on, GPS is actually quite hard to get. But some folk do. They run little antennas out the back and they pull down time from these spacecraft. And what we then use is a protocol, the network time protocol, that sends that time around the network. So let's look at that network protocol for a second. Some of you who have tried to configure this up in your networks this would start to become pretty familiar. If you're actually running a GPS receiver and sending time out, you're reliable. You're stratum 0 because you are a reference clock. If I receive your signals, Brandy's correcting me in saying I'm stratum. Okay, yeah, you're right. Stratum 1 is directly connected to that reference clock source. Stratum 2 sends that out as a second rumor from the first. So there's a hierarchy of strata. The way the protocol works is blindingly simple. The client puts the time in a packet and sends it to the server. The server records its time when it received the packet. It adds its time into the packet and sends it back to the client, who adds the time it got the packet. So now each of these packets have 4 times. The time it left, the time it arrived, the time it left over there, the time it arrived back to me. There's a packet. Now, I don't want to go through how NTP works, But I want to point out one thing. The time is universal coordinated time. It doesn't matter where you are on this planet or not. If you're running NTP, the time in that NTP packet is the same for everyone. It's the single base time. Local time is just stuff you add on for humans. It has nothing to do with the underlying time. So NTP runs the standard universal coordinated time. So most of the time, NTP is one of the most amazingly cool protocols around. It only does a packet exchange every 16 seconds, which in this day and age of DNS is just such astonishing restraint. Maybe it should be taken out the back and fired, and shot, because, everything else just blasts the network. If you run out of sync, NTP will throb a bit harder to try and bring you back, and it will burst 8 packets, evenly across that 16-second interval. But most of the time, if you're in sync, NTP just does this very quiet baseline exchange of packets. It'll skew the time slowly. It'll bring you back in at about half a millisecond per second. So if you're way out of time, it will take some time for the machine to come back, but it will come back. The reason why it does this, by the way, is we found in a number of leap seconds, there was a brilliant leap second where the entire Sabre airline reservation system crashed because, 1 second managed to fatally confuse the underlying system. Alarms went into kernel panic mode, machines crashed, horrible things. So now we've learned better, skew the time slowly. NTP is really good. This process keeps almost everyone within a few hundredths of a second to each other. Or does it? So that was this introduction to the fact that A, we understand time pretty well, and B, we actually really understand how to distribute time. So all of these 20, 30 billion devices that have some awareness of the time on the internet actually have even more than that. They're bloody good at it. They have an awareness of time within a tenth of a second or so. Isn't that amazing? I think it's amazing. So we thought we'd test this theory because, we can. We run an online ad, and a lot of this ad we do is we ask folk to report back if they can do V6. We ask them to report if they can do DNSSEC. We ask them all kinds of things. We use JavaScript, HTML5, inside the client's machine to drop back some information to our servers. One of the calls that is supported, thank you Google, is actually a JavaScript operation called getTime. So we actually ask the end user, who hates the ad, what's your time? Not what's your local time, don't care. What's your UTC time? And we record the differences between what they say the time is and what the time on our server is, because we're running UTC time as well. Now, I don't care about propagation delays, so I'm going to ignore the milliseconds. I'm only interested in the seconds. But I'm interested in more than that. I'm interested in days. Now, remember I said that Google's certificate is 30 days. So that if you're more than 30 days out of whack, if you think the time is further than April 23, then you've got trouble. All these people here, because that unit is days, are reporting a clock value which is 200 days in the future. I'm stunned. Even going back, now this is a log scale, don't forget it's log scale, but there are a significant number of folk who have drifted out and somehow are living in 2018. Some of them, I believe, are in 2017 still because it was so cool then. This is totally unexpected, completely wacko. So start to look a little bit harder. The first thing is it's a log scale. And don't forget, what is big in a log scale is not that big. So we are talking about the lunatic subset, okay? Most of you are fine. Most of you roughly agree on the time, but a small number of you are just completely wacko. How wacko? Well, we tested an awful lot of folk, 202 million of them over an 80-day period. 11% are more than 1 second fast, which I think is actually a really big number. It shouldn't be that high. 57% are more than 1 second slow. Clock slews are out by up to more than a year. Wow. 92% are at least within 2 minutes, which for NTP is pretty bad. 120 seconds is not a very good thing to work off. But, that's what we found. So here is the distribution of people who are fast. They're ahead by more than 2 days, but there's something really odd about that distribution. There's an awful lot of folk who are out by 2 days, 3 days, 4 days, 5 days. They've got the seconds right, they've got the hours right, but the days wrong. How could you possibly do that? Someone's going to put their hand up. It was me. Somebody has just managed to completely confuse themselves. Now, don't forget, NTP talks universal coordinated time. So whoever has managed to get their clock, their UTC clock, out by a precise multiple of 86,400 seconds actually deserves a medal. Because that is creative programming that I just can't conceive how you can be so wildly wrong yet perversely right at the same point. But it gets weirder, because then I started to look at hours. And not only are there a bunch of folk who get it wrong by days, there are a bunch of folk who get the seconds right but the hours wrong. And there are quite a lot of them. There's 1 hour, 2 hours, 3 hours, 4 hours. There's a whole bunch of machines that slew by 1 hour precisely. There's more coming. It gets weirder. Oh, you do it all the time. Let's look at slow. I expect that kind of offset because of lost interrupts. Slow is easy to understand. There's stepping functions going on, and if you blow it up, you can see it quite clearly. There are step functions. So now I'm getting really curious. What if I ignore the seconds? And ignore the hours and the days, and simply say, if you're out, how many seconds are you out from my reference time? There's an awful lot of folk who are actually bang on the same second but wrong by hours. And there's a second bunch of folk who are wrong by half an hour. So not only is some perverse bunch of folk getting the 84,600 wrong, there's another bunch of folk who've got their clock out by 43,200. Now I'm getting impressed with this. There is something about local time and UTC time that is confusing a lot of people. Okay? And so someone said, well, can you look? Because local time and UTC are getting confused. Now, the one thing I know when I asked these people for the time was they told me their IP address, which could have been a big mistake, but it came in on the packet. It was part of the header. I just happened to listen. And I run a pretty standard geolocation. I use MaxMind. It's basically accurate, give or take about 5%, but good enough. So I know where these people are, and I know the ones whose clocks are off. So let's take one. This is Brazil. The local time, because Brazil's a big country, spans -2, -3, -4, -5. But most people live in -2. And most people in Brazil have daylight savings time. And this was done in southern summer. And so I expect a peak at UTC -1. And yes, local time and UTC time are getting really confused in Brazil. There's a bunch of folk who are out by an hour. Some folk don't know the difference between plus and minus. And there's a bunch of people in Brazil who think they're in Germany or Spain or somewhere else that is 1 hour the other side of UTC. Fine, I can forgive that. But there's some strong correlation that when I asked for UTC time, they gave me local time. So let's go to India. A lot of people in India. India is one of the few countries that decided in its perverse brilliance that it would have a standard local time offset by 5.5 hours. I don't know if it was just to annoy the computer scientists around in the world or whatever, but that was their call, that was what they did. Now, if you look at the distribution now, all of a sudden, all the half hours peak. Now, India's time is up 5 hours and 30 minutes from UTC. 5 hours and 30 minutes. So what the hell is going on way back at this other peak of minus 6 hours and 30 minutes? In fact, why is every peak in India offset by 30 minutes? It's kind of, yeah, I know we're 30 minutes off. Bugger about the hours, but we're 30 minutes off. So the whole reason why there were 30-minute peaks in this data set was actually all due to India. Thanks, guys. And last and not least, China. Local time is UTC plus 8, right? UTC plus 8, not UTC minus 8, which is that peak over there. Again, I have no idea what's going on, but I'm amazed about plus and minus. And the other thing too, there's this huge sort of cluster around UTC out by 1 hour or so. So again, sort of what I expected, sort of not. So is local time and coordinated time getting confused with some of these systems? I'd say at about 10 to 20% of the cases it is. But the rest of it, there's some kind of deviant, bizarre, perverse brilliance in being able to create a clock that is wrong in the hour, even wrong in the day, but bloody hell, it's got the seconds right. That I have to applaud, if not cry over. So, if you really want to do short-lived certificates, it's not going to work. Only 58% of people run their clocks within 2 seconds of real time. So if you want something to happen and you're relying on the fact we all understand the same time, you'll be wrong almost half the time. If you're able to say within the same minute, you'll get about 92% within the same minute. And if you're willing to say 1 hour, we're all running within 1 hour, except those 2% of deviants who wouldn't have a clue what the time is. So if you really are doing certificate work and you really want to time things, just remember, we don't agree on the time. You'd probably be unwise to think we can get it within an hour. You probably need to work in days, and that would be the more robust way of doing it. Thank you. Any questions?
Randy Bush. Jeff, don't you get a server fingerprint?
Sorry?
Don't you get a server fingerprint?
A server fingerprint. Yes, I do. And the bastards lie so often, it's really hard to understand what I'm seeing here. I do not see a consistent fingerprint of the ones that are out. In other words, that same fingerprint gives me accurate. And so I am now left in this strange world, Randy, that I think some stratum 1 and 2 sources are lying. And they're actually offering local time, representing it as UTC. This explains why India is consistently so weirdly out by 30 minutes. So I think the problem is actually not in the client getting things confused. I actually think it's in the rather haphazard way a lot of operators treat stratum time signals and have misconfigured their servers.
I think you missed the memo that Trump declared that everything goes on East Coast U.S. time.
Thank you. You're right.
Jeff.
Yeah, hi.
Possible explanation. Jordi Palet. When you're running some virtualization environments like ESXi from VMware, you should keep the server in UTC. If you make the mistake of changing that, the NTP server that is running on the host of the virtual machine is lying to all the clients in that network. You see the point?
Right, so if my host gets it wrong, all the clients get it wrong too.
Exactly.
And for the host to get it wrong, it's local time, not UTC time.
The host will get the same wrong information that the server has been configured. So all the hosts in that network will get the wrong information. If you are using one of the virtual machines to be the NTP server for the rest of the network, you are getting all wrong.
So what amazes me is I'm doing an ad using HTTPS, in theory. And these folk are reporting times that are up to a year out. I have no idea why they think the certificates that got exchanged were valid when, according to their own representation of the clock, they're not. So it might well be part of that, but there's something even more bizarre about the time they're reporting back versus the time they're using in the cert validation and other processes.
Right.
I'm just impressed at how subtle this problem is, yeah.
Jeff Osborne.
Hi.
Jeff, did you try using any country in which the local time was UTC, and did you get zip for a delta?
Wow. Good question. I didn't, but thank you. It's gathering data every day. I don't. Frank.
Yeah. So a couple of comments. I used to live in Fiji, and then one day they decided that next week they are going to change their time zone. So the time of propagation of the time zone database didn't happen. And here I was trying to configure two servers with two different versions of Windows. One I could push a new time zone, the other one I couldn't push it, and trying to get them to synchronize. And they couldn't get the right time. I had to play and find a time zone that was mutually agreeable. So my feeling is that countries that change time zone and the time zone file does not get propagated create troubles on the UTC clock.
So this is where my puzzled look comes in.
I had
Because in
this
some
issue a
ways-
long time ago, but I hope
Right.
that by now it's fixed, but then you've got a lot of false operating system everywhere.
Local time and time zones are merely cosmetic for humans.
It's supposed to be.
Yes, in theory, underneath this is this UTC time substrate. And in theory, you know, I should be able to flip time zones at ease because it's merely a presentation format. The underlying time is UTC. That's the theory. But what you're saying is, in practice, the world is far weirder, messier, and sillier than that.
Yeah. Also on the GPS, the time that the GPS gives needs to be corrected because the leap second are not applied to the GPS clock.
I wasn't looking down at that level of millisecond and nanoseconds. You're right, but I wasn't looking down.
There's several seconds that are different between the GPS clock and the UTC clock time.
Oh,
Because the leap second is never applied to the satellite.
Right.
Finally, NTP, if it's on the IPv6, it doesn't fall back to IPv4.
I'll leave that one where it is. Tashi.
Hi, Jeff Tashi
Hi.
here. Borrowing from Randy's thing, would fingerprinting the client OS have you done?
I've done a certain amount of fingerprinting and I didn't find any solid clue, which is what led me to the observation that if local time and UTC time are getting confused, it's not necessarily the client that's doing the confusion. The NTP stratum, something that you're syncing against, might be confusing you and actually giving you an incorrect UTC time, which you're then faithfully reporting, which is why some folk with the same SIGs will give me back different times, even if they're in the same country and theoretically in the same time zone. They're getting their time from a different source. And I can't see their stratum. I don't know where they're getting their time from. The ads don't give you that. But yeah, it's a fascinating area. Thank you. No other questions? Thank you.
Thank you very much, Jeff. So that brings us to the end of the first Apops session. So just a few reminders before we go. Call for lightning talks is open. So we have had about 8 or 9 of them so far proposed. So the PC will pick the best 8 or 9 or 10 or however long the authors claim they're going to talk. Along with that, we also have on Thursday a NOG updates session. So any network operators group would like to update on what they're doing or what's happening with their operator group. Of course, priority given to those from the Asia and Pacific regions, but we welcome any presentation from operator groups from outside Asia Pacific as well. So look forward to getting those submissions. So we'll fill those on Thursday. We'll let you all know by Wednesday evening if your talk makes it or not. Social event, I believe the doors open about 6:30 or so. Formally it starts at 7 o'clock and we have welcome. Soon after that, the social event is hosted by Kisti, who is, sponsored by Kisti, who is our host here. Don't forget to collect your tickets if you don't already have entries by ticket, because it's actually a limited number of limited space. So if you're not planning to go, please will you give your ticket to somebody who wants to go but doesn't have one. Otherwise, that's the end of the Apops session. We start again tomorrow morning with K-pop at 7:30, if you want to do that. Otherwise, 9:30 a.m. for the second Apop session in this room here, by which time we should have good projectors and brighter lights. See you all tomorrow, if I don't see you this evening. Thank you. We don't need to. We're okay.